Hey everybody, in this next video lesson, we're going to talk about something called Gibbs free energy, or just free energy. We're also going to talk about how to calculate standard free energy for a particular reaction, given the free energy of the reactants and products of any given chemical reaction. The calculation of Gibbs free energy helps us determine whether or not something is going to happen spontaneously or non-spontaneously. Remember back at the end of video lesson number 1, we talked about how scientists used to think that anything that was exothermic was spontaneous, and anything that was endothermic was non-spontaneous. But we know that there are some things that are endothermic that do happen spontaneously. So enthalpy, or delta H, can't be the only indicator to determine whether or not something happens spontaneously or non-spontaneously. Enthalpy alone cannot be your only determining factor. Well, we told you also in that first video lesson that entropy plays a role. Gibbs free energy, or the calculation of Gibbs free energy, allows us to determine whether or not something happens spontaneously or non-spontaneously, factoring in both enthalpy and entropy. Now, the reading in this happens on page 803 in the textbook, but the calculation is rather simple. Gibbs free energy is identified by delta G. Delta G is equal to delta H minus T times delta S, where delta H is the enthalpy, usually measured in kilojoules, and T is the absolute temperature measured in Kelvin. And delta S is the entropy, and that's measured in joules per Kelvin. And if you just simply take these two and add them up, the enthalpy and the entropy multiplied by the temperature, you get Gibbs free energy. Gibbs free energy, or free energy, is often measured in just kilojoules. Now notice that enthalpy is in kilojoules and entropy is in joules. And so when you're going to calculate these, you got to make sure that after multiplying your entropy times per Kelvin, that you convert the joules to kilojoules so that when you add them together, that the units are consistent. Because delta G in the end has to also be in kilojoules. And so watch out for that. Convert your entropy to kilojoules before multiplying it by the temperature in order to make sure that the units are consistent. Now, to determine if something happens spontaneously or non-spontaneously, we simply need to look at the sign of the delta G. If the delta G is negative, then this situation happens spontaneously in the forward. If delta G has a sign that's positive, then it's non-spontaneous in the forward. And every once in a while, and it's pretty rare, but if delta G is calculated to be 0, then that chemical reaction or physical process is at equilibrium. Although that happens, the first two are the most likely scenarios, either negative delta G or positive delta G. I'd also like to talk to you about the concept of thermodynamic favorability. You might come across this term on the AP tests or even in the text. Anytime that something is considered to be thermodynamically favorable, what they're really meaning is that it has a negative delta G value. So if delta G is negative, we consider that thermodynamically favorable. To put it another way, thermodynamically favorable means that the situation is happening spontaneously in the forward direction. Now you might be noticing that I'm saying things like in the forward direction. And as you'd probably expect, equilibrium, or the concept of dynamic equilibrium, plays a very close role in Gibbs free energy, or free energy. And we'll talk about the connection between equilibrium and free energy in the next video lesson. Now I'd like to free up a little bit of room here and talk about a situation, a specific one, in a chemical reaction that comes directly from the book. Let's take, for example, that we have N2 gas and O2 gas coming together to make NO gas. And the chemical reaction looks like this. Now the enthalpy for this reaction is endothermic. It's positive 180.7 kilojoules of energy. That means that this reaction requires energy in order to happen. It absorbs energy. Now the entropy of this situation is also a positive value. It's positive 24.7 joules per Kelvin, which means that this reaction, although it looks like it's about the same in entropy because we have equal moles of gas on the left and the right, is slightly positive, which means it's slightly entropic, or favors disorder. Now the temperature that this happens is 298 Kelvin. Now we want to quickly calculate the delta G. Well, we just simply take 180.7 kilojoules of energy, subtract 298 times 0.0247 kilojoules per Kelvin. Do you see how I converted the entropy to kilojoules before I added it together to make sure that the energy units are consistent with one another? Well, 298 multiplied by 0.0247 kilojoules of energy and then subtracted from 180.7 kilojoules gives me a delta G value of 176 kilojoules. Now notice that the sign for delta G for this particular situation is positive 176 kilojoules. That means that this reaction is not spontaneous in the forward reaction. That means also that it's not thermodynamically favorable to happen. What that does mean is that the reverse reaction is thermodynamically favorable. And if you reverse this reaction, then you just simply flip the sign of delta G. And so the opposite reaction is negative 176 kilojoules, which means that is the spontaneous of the two situations. Now I'd like to talk about calculating standard free energy. Once again, standard means that we're at 1 atmosphere pressure and 298 Kelvin. Now we're going to calculate standard free energy the same way we calculated standard enthalpy or standard entropy. Standard free energy of a reaction is calculated by taking the sum of the moles times the free energy of the products minus the sum of the moles times the free energy of the reactants. Free energy is like enthalpy in that the free energy for any element or diatomic molecule in its standard state of matter is equal to 0. Remember, entropy can only be 0 when the temperature is 0 Kelvin, and so you'll never see a standard entropy equals 0. But for enthalpy and free energy, it's possible to see a value of 0 if it's an element, for example, like aluminum in its solid state, or maybe chlorine, which is Cl2 in its gaseous state. Both of those would have a free energy equal to 0. But these free energy values for individual elements or molecules or compounds can be found in data tables at the end of the textbook or by simply looking them up online. Let's do a quick calculation of standard free energy using the information provided. We've got a chemical reaction. P4 plus 6Cl2 gives us 4 PCl3. Now here are the Gibbs free energies, or free energies, for the following. We've got negative 269.6 for the P4. Chlorine, as we mentioned before, since it's in its elemental state of matter, is 0. And then PCl3 is positive 24.4 kilojoules per mole. So I start with the products first. I take 4 moles times the negative 269.6 kilojoules per mole, and the moles cancel each other out. Then I take that and subtract the 1 mole of the P4 times its free energy of positive 24.4 kilojoules per mole. And since Cl2 has 0, then it doesn't really matter because anything times 0 is 0. Now if I take these two numbers and multiply them together, and I take these two numbers and multiply them together, and then I add up the resulting values, I get a positive 367.2 kilojoules of energy, which means that this is a non-spontaneous situation and is not thermodynamically favorable. Now take a look at this problem. Sometimes you're not actually asked to calculate the free energy of a certain situation, but rather just talk about it qualitatively. And so predict whether the delta G of this reaction will become more or less negative. Notice it's not asking you to calculate. It's asking it, will it become more negative, meaning more thermodynamically favorable, or less negative, less thermodynamically favorable. Less negative, remember, means closer to 0. So tell us whether or not the delta G will be more or less negative than the delta H for the following reaction. Keep in mind that the clues to whether delta S is positive or negative. Remember, if you have more moles of gas on the left than you do on the right, then the delta S is a negative because you are creating less moles of gas, and that means that the pressure is going down and becoming more ordered. In this case, you've got 1 plus 5 or 6 moles of gas on the left, and you've got 3 plus 4 or 7. So the moles of gas are increasing, and so in this case, delta S is positive because there is more disorder. Now consider the formula for free energy. Delta G equals delta H minus T delta S. And if we know that delta H is negative because it shows it right here, and we know that the delta S is positive, well then we're going to subtract a positive number. Or in other words, when we take delta H and subtract a positive number, then we are going to become more negative. So to answer the question up above, delta G will become more negative in this situation because the entropy is increasing. Now, if for some reason the delta S for this particular situation was negative, then it would be subtracting a negative. So that's the same as adding. And if in this case, if the delta S was negative, then the delta G would become less negative or closer to 0. But in this case, since delta S is positive, it is becoming more negative. I'd like you to consider table 19.3, and I grabbed a screenshot of it right from the textbook and plopped it in here. And it talks about how the effects of delta H and delta S and the signs of those will affect the spontaneity of the reaction. We'll first start here with a negative delta H and a positive delta S. Negative delta H, as we mentioned before, favors a spontaneous reaction. So does a positive delta S. And so if you've got negative delta H and a positive delta S, then you'll see that the reaction characteristics say that it's spontaneous at all temperatures. Now, if you reverse the situation and you have a positive delta H, well, that favors a non-spontaneous situation. So does a negative delta S. When you become more ordered, that is favoring the non-spontaneous situation. So if you flip the signs to be positive for delta H and negative for delta S, then that would favor a non-spontaneous situation at all temperatures. Now, what you need to look out for is when the signs of delta H and delta S are the same. If they're both negative, then the reaction characteristics favor a spontaneous situation at low temperatures. I drew in the formula for calculating delta G here at the bottom. And if delta H is negative, well, then that favors the spontaneous in the forward because exothermic favors the spontaneous. But you're going to then subtract a negative delta S, which favors the non-spontaneous situation. But you are subtracting a negative, which is the same as adding. And so as the temperature increases, the T times delta S gets to be a larger value, and you're adding, because you're subtracting a negative, or you're adding a larger and larger number. And eventually, as temperature gets high enough, that eventually multiplies by delta S to become larger than your negative delta H. And so a high temperature will overtake the negative delta H to flip the sign of delta G at high temperatures, making it non-spontaneous at high temperatures. Again, I'd like to talk about what happens when you've got the same sign for both enthalpy and the entropy. Now consider both positives for the enthalpy, which favors the non-spontaneous when it comes to enthalpy, but entropy that's positive favors the spontaneous. So you've got a delta H value that's positive, and that means typically then it's non-spontaneous. But if you take and subtract a positive number from that positive entropy, then as the temperature goes up, this T times delta S term becomes larger and larger and larger. Or in other words, you're subtracting a larger and larger value. And eventually, as the temperature gets high enough, you're going to subtract a number large enough that it's going to flip the sign of delta G from positive to negative. And once that happens, at high temperatures, the delta G goes from non-spontaneous to spontaneous, which is why we say that when delta H and delta S are both positive, that it's spontaneous at high temperatures, because then you are subtracting a larger number, T times delta S, from a smaller positive delta H value here, resulting in a negative delta G. One of the favorite types of questions that the College Board likes to talk about is not necessarily calculate delta G, because as you can see, it's a fairly simple and straightforward. But they'll ask you to tell or predict what will happen to delta G if you change the temperature. And you need to factor in the signs of both the enthalpy and the entropy in order to figure out what's going to happen in that situation. So watch out for those different combinations of delta S and delta H and pay very close attention to the signs. Well, that takes care of this video lesson about free energy. Thanks for watching.